Fourier transforms. When f of x is a periodic function, we already discussed it. We can write that one as Fourier series expansion in the interval minus L to L. When f of x is periodic function, interval is minus L to L. Now the same topic we are extending to non-periodic functions and interval is minus infinity to infinity. A function which is not periodic and the interval is minus infinity to infinity, that can be expressed as Fourier integral. So that is, from that Fourier integral we can find Fourier transform. What is actually integral transform? From this only we are going to discuss Laplace transform, Fourier transform, Z transform. This is the basic formula for integral transform. So the integral transform of f of x we represent like this. Integral transform of f of t. This I will be, if it is Fourier we will write f, if it is Laplace we will write L, if it is Z transform we will write Z here. Now I am writing the common formula for integral transforms. Integral transform of f of t is represented like this. Integral a to b f of t into k of p comma t dt, in which k of p comma t is called kernel. So depending on that kernel, we will decide whether the function is Fourier or Laplace. If it is e power minus st, we will call that one as, when limits are 0 to infinity, this is e power minus st, we call that one as Laplace transform. When the limits are 0 to infinity, when kernel is k of p comma t is, now we are going to discuss e power ipx, we call that one as Fourier transform. So this is the basic integral transform formula from which all transforms were derived. Now we are going to discuss what is Fourier transform. Fourier transform. Fourier transform of f of x is, we represent this one like this, capital F of x or capital F of p, which is integral minus infinity to infinity f of x into e power ipx dx. The kernel for Fourier transform, that is k of p comma t, is e power ipx. For Laplace transform, e power minus pt, in terms of p, in terms of s, e power minus st. Now this is Fourier transform. If you want to find inverse Fourier transform, inverse Fourier transform, that means reverse what I written just now. That means finding f of x when f of p known. So small f of x is equal to inverse Fourier transform 1 by 2 pi integral minus infinity to infinity capital F of p into e power minus ipx dp, because function is in terms of p. This is formula to evaluate inverse Fourier transform. So what is the existence, what are the conditions, necessary condition for existence of Fourier transform? We call them as Dirichlet conditions. Dirichlet conditions for existence of Fourier transform. There are two most important points. One is the function should be single variable. That means in terms of t or in terms of x, one variable function, and f of x and f dash of x are piecewise continuous. Piecewise continuous. Then only one can easily find out Fourier transform for given function. Here there is no mandatory case the function is periodic. In Fourier series, f of x should be periodic. The interval is minus L to L. Other than minus infinity, infinity we can't do there. Here interval we may take minus infinity, infinity, but function should be single variable, and f of x, f dash of x are piecewise continuous. Then we can find Fourier transform for any function. This is Fourier transform, inverse Fourier transform. For example, if you want to find Fourier cosine and sine transform, Fourier sine transform and cosine transform if you want to find. We represent these like this: S of f of x or fs of p. Fs of p. S represents sine, Fourier sine transform. Fourier sine transform has formula integral 0 to infinity f of x into sine px dx. Sine px. Inverse Fourier sine transform. Inverse Fourier sine transform. That means when fs of p is given to find f of x, f of x is equal to 2 by pi integral 0 to infinity fs of p, because sine transform of function is given, fs of p into sine px dt. With respect to p we need to do for inverse sine. Similarly, Fourier cosine transform. Fourier cosine transform of f of x is given by, this is sine, this is cosine. Fc, c represent cosine. Fc of f of x is equal to Fc of p, which is the same one, integral 0 to infinity f of x cos px dx. Inverse Fourier cosine transform. Inverse Fourier cosine transform is given like this: small f of x equal to, same like previous, integral 0 to infinity fc of p into cos px dp. So this is inverse Fourier cosine. So these are the formulas we are going to use to find Fourier transform, Fourier sine transform, Fourier cosine transform. Then you may have wondered what is the use of Fourier transforms, applications or uses. So this one we can use in ECE course subject. There is one subject in engineering, ECE branch, electronics and communication engineering. There is a subject, signals and systems, which discuss about signals. To find out the nature of signal, to find out the frequency conversion in signals, we are going to use complete Fourier transform. If you are an ECE student, without having knowledge of Fourier transform, you cannot understand this subject. One subject is there in ECE which plays key role. Nowadays, without signals, there is no electronic device. So there, this Fourier transform plays key role in engineering. Okay, so Fourier transform of f of x is this one, inverse is this one, and the limitations, the conditions for existence of Fourier transform are these two, and Fourier sine transform, cosine, inverse Fourier sine and cosine. Any doubts you may express. Linear property of Fourier transform. F of p, f of capital P, comma, g of p are Fourier transform of f of x, comma, g of x. Then capital F of a into f of x plus b into g of x equal to a into f of p plus b into g of p. A into f of p plus b into g of p. This is the linear property of Fourier transform. This we are going to prove how we get that property. We all know that, and given Fourier transform of f of x is f of p, Fourier transform of g of x is g of p. What is actual Fourier transform of f of x and g of x? Fourier transform of f of x is capital F of x. We represent this one like capital F of p, which is equal to integral minus infinity to infinity e power ipx into f of x dx. Similarly, Fourier transform of g of x is capital G of x equal to capital G of p, which is integral minus infinity to infinity e power ipx into g of x dx. Okay. Now what we need to find? Capital F of a into f of x plus b into g of x equal to, same, this is f of x. Here in the place of f of x we need to replace with this term in Fourier transform of f of x or g of x. Here what you are having, in this place you are having this term, simply replace this term here. So what you will get? Integral minus infinity to infinity e power ipx into a into f of x plus b into g of x dx. Now split that integral. Integral minus infinity to infinity, take a constant, a into e power ipx into f of x dx plus b integral minus infinity to infinity e power ipx into g of x dx. So a into this value integral minus infinity to infinity e power ipx into f of x dx is capital F of p plus b into this value is capital G of p. Okay, this is the linear property of Fourier transform. So shifting property of Fourier transform. So if f of p is Fourier transform of f of x, then we need to prove that f of x minus a is e power ipa into f of p. Fourier transform of f of x minus a is this one. To prove this, first write what is Fourier transform of f of x. Fourier transform of f of x is capital F of x, which we are calling as f of p, integral minus infinity to infinity e power ipx into f of x dx. But what we need to find this value? Capital F of x minus a equal to integral minus infinity to infinity e power ipx into f of x minus a dx. So to get this form, simply we are taking x minus a as t. So differentiation of x is dt. From this x is t plus a. So limits are infinity minus infinity. Limits are same. Limits will be same. So integral minus infinity to infinity e power ip into t plus a f of x minus a is t, f of t dt. Now separate this one. This will be e power ipt into e power ipa. You can take e power ipa as constant because we don't have t terms. This can be written like this: e power ipa into e power ipt. So here in this we don't have t terms. You can keep that one as constant like this. Integral minus infinity to infinity e power ipt into f of t dt. Okay, what is integral e power ipx into f of x dx? F of p. So in the place of x we are having t. Both integrals are same. Simply one variable is different. So we all know that with same limits, if you change the limit, if you change the variable, that integral value is same. What I am saying, integral a to b f of x dx equal to integral a to b g of t dt. So like this, we can treat this one as f of p, which we need to prove. E power a p a f of p we need to prove. Okay? Any doubts in the expense? So modulation theorem on Fourier transform. The statement of modulation theorem is, if f of p is Fourier transform of f of x, then Fourier transform of f of x cos ax, f of x cos ax is 1 by 2 into f of p plus a plus f of p minus a. So which can be written like this, that is capital f of x into cos ax is f of x into cos ax is 1 by 2 into f of p plus a plus f of p minus a. So this is Fourier transform of f of x cos ax we need to prove now. So to prove this, we all know that Fourier transform of f of x is capital f of x, which is equal to capital F of p integral minus infinity to infinity e power ipx into f of x dx. Now we need to find Fourier transform of f of x cos ax dx. That is integral minus infinity to infinity e power ipx into cos ax dx f of x cos ax dx. Here in the place of f of x we are having this one, that one we are going to replace in the place of f of x. Now we all know that cos ax can be written as e power ax plus e power minus ax by 2. E power ax plus e power minus ax by 2. E power iax e power minus iax by 2 cos ax. Cos ax can be written like this. Substituting that one here, what you will get? Integral minus infinity to infinity e power ipx into f of x e power iax plus e power minus iax by 2. So take that 1 by 2 as constant. Now split this integral into two integrals. Integral minus infinity to infinity e power ipx and e power iax. E power ipx and e power iax bases are equal. You can add exponents and ix are common. So you can write like this, I into p plus a f of x. P plus a x, I and x are common. In ipx and iax, ix are common, the leftover is p plus a. F of x dx, one integral, plus integral minus infinity to infinity, second one. If you see the second one, ipx minus iax. Here also ix common, but here p, here minus a. P minus a you are having. E minus a into x. F of x dx. So 1 by 2 into, here e power ipx f of x dx is capital F of p. The same one, in the place of p you are having p plus a. Then you need to replace p with p plus a, f of p plus a plus f of p minus a. So this is modulation theorem in Fourier transform, simply finding Fourier transform of f of x cos ax. Okay. Find Fourier transform of f of x defined by f of x equal to 1 when mod x less than a, 0 when mod x greater than a, and hence deduce these values also. So to deduce any derivation in Fourier transform, after finding Fourier transform, you need to use inverse Fourier transform formula. So this problem is especially very most important. So many times we got in external. Important problem. So we can easily find, and easy also. We can easily find Fourier transform of f of x because f of x is 1 constant function, simply 1. We all know that what is Fourier transform of f of x. Fourier transform of f of x is capital F of small f of x, which is we denote like capital F of p, integral minus infinity to infinity e power ipx into f of x dx. But our interval is mod x less than a. Mod x less than a means minus a less than or equal to x less than or equal to a. That means interval is minus a to a. In other intervals that becomes 0. That's why in that interval we are taking Fourier transform minus a to a e power ipx into f of x is 1. Integral ipx e power ipx by ip, x coefficient you will get. Integral e power ax by a. So e power ipx by ip minus a to a. So if you write in the place of x a first, you will get e power ipa. If you write 1 by ip is constant. If you write in the place of x minus a, e power minus ipa you will get. So 1 by ip into, so you know that e power ix minus e power minus ix can be written as 2 sin h ax. So like that, here this can be written sin 2 sin h ipa 2 sin h ipa, this value. So this is formula we are using here, e power iax minus e power minus iax can be written as sin hx hax. Using that formula we can write this one like this. E power ax means you know cos ax plus I sin ax. Using this we are writing cos ax minus I sin ax. So using this formula we are replacing that one with 2 sin h ipa. Again we know this sin h ix. Sin h of ix if you have, this can be written I sin x. Sin h of ix can be written as I sin x. This is the important one. This we are using here to cancel this side. So what you will get? 2 sin pa I 2 sin pa by ip. So ia cancel. You will have 2 sin pa by p. This is Fourier transform of f of x, the first part. First part of the given problem, Fourier transform of 1 is, that is p is 1. Fourier transform of 1 is 2 sin pa by p. Now we need to derive the remaining 2. To derive that, using inverse Fourier transform. Inverse Fourier transform. Using inverse Fourier transform, small f of x equal to 1 by 2 pi integral minus infinity to infinity e power minus ipx into f of p dp. So here f of p means this one, 2 sin pa by p, 1 by 2 pi integral minus infinity to infinity f of p e power minus ipx, f of p is 2 sin pa by p dp. Okay, now e power minus iax is cos ax minus I sin ax. This is standard formula. So using that formula, we are writing this one as 1 by 2 pi into integral minus infinity to infinity cos px minus I sin px into, you can cancel this 2 here itself, 1 by pi cos px minus I sin px sin pa by p dp. Now multiply 1 by pi into integral minus infinity to infinity cos px sin pa by p dp minus I into integral minus infinity to infinity sin px into sin pa by p dp. So we all know this formula in integration. Integral minus infinity to infinity f of x dx is 0 if f of x is odd, 2 integral 0 to a f of x dx if f of x is even. So odd means x cube, even means x square x power 4. So if you have two odd terms like this is in p, sin is odd, here p is odd, sin px by p sin pa dp. If you have like that, the sin terms becomes an odd function. So what happens? Sin is odd, cos is even. This complete function becomes odd, this value becomes 0. This is even. This won't be 0 now. Now f of x value we know, f of x is 1. That means LHS side you are having 1. If you send that pi to this side, you will get integral minus infinity to infinity cos px into sin pa by p dp equal to pi for mod x greater than a, 0 for mod x less than a. This is this part, this value. Next we need to find sin p by p dp, integral 0 to infinity. To find sin p by p dp, this cos should be 1. When cos becomes 1, if you write in the place of x 0, cos 0 1. So if you keep x 0, then what happens? Integral minus infinity to infinity, cos becomes 1. Sin pa by p dp equal to this value, pi. Okay. But this is even. If it is even, we can write like this, 2 integral 0 to a. So now this can be written like this, 2 integral 0 to infinity sin pa by p dp is this one. So if we send this 2 to that side, that becomes pi by 2, 0 otherwise. So these two values we need to find. One is sin pa by p dp and this value is pi. And Fourier transform of 1 is this one. So these we are going to evaluate using inverse Fourier transform. Whenever if you have derivation in Fourier transform, you have to use inverse Fourier transform. Okay, any doubts you may express. Find Fourier transform of e power minus a mod x, a greater than 0, and hence show that integral 0 to infinity cos px by a square plus p square dp equal to pi by 2a e power minus a mod x. So first we need to find the Fourier transform of this one. Next we need to show this value. To derive that one, we need to use inverse Fourier transform after finding Fourier transform of this function. So first of all, we are going to find Fourier transform of e power minus a mod x. For that, so let f of x, we are taking this one as f of x for a greater than 0. Next, Fourier transform of f of x is capital F of small f of x, which can be written like this: integral minus infinity to infinity f of x into e power ipx dx. Here f of x is e power minus a mod x. Integral minus infinity to infinity e power minus a mod x. E power iax, you know this formula? E power iax can be written as cos ax plus I sin ax. Using this formula, we are writing this one like this: cos px plus I sin px into dx. Now multiply and split the integral into two integrals like this: integral minus infinity to infinity e power minus a mod x cos px dx plus integral minus infinity to infinity e power minus a mod x, here I is there, sin px dx. We all know that cos is even, sin is odd. In integral minus a to a, if f of x is odd function, then that integral value is 0. This is odd, this becomes 0. This is even, this is non-zero. This formula already we discussed. This is the formula I am using here. Integral minus a to a f of x dx equal to 0 when f of x is odd, to integral 0 to a f of x dx when f of x is even. So if it is odd function, we can write that value 0. Even, we will write this integral like this: 2 integral 0 to a, 2 integral 0 to infinity e power minus a. We all know that mod x is plus x in 0 to infinity, and this value is minus x minus infinity to 0. So here the interval is 0 to infinity, mod x becomes plus x. So e power minus ax cos px dx. So this is direct formula: integral 0 to infinity, this is also formula, integral 0 to infinity e power ax into cos bx dx. Direct formula: integral 0 to infinity e power ax into cos bx dx. We can keep that one as formula directly, which can be written like this: a by a square plus b square. This is also formula. These are all formulas. Now this can be written like this: here in the place of a we are having a e power minus ax only. In the place of a we are having a, so 2 into a by a square plus p square. 2 into a by a square plus p square. This is capital F of p. Capital F of x can be written like this: capital F of p equal to 2a by a square plus p square. This is Fourier transform of e power minus a mod x. Fourier transform of e power minus a mod x is 2a by a square plus p square. Next we need to derive this one. To derive this one, this is Fourier transform, we need to derive that one. To derive that one, we need to use inverse Fourier transform. Inverse Fourier transform of f of p. It means small f of x equal to inverse Fourier transform formula of f of x equal to 1 by 2 pi integral minus infinity to infinity f of p into e power minus ipx dp. E power minus ipx dp. Excuse me. e power minus ipx dp. This is the formula. Excuse me. 1 by 2 pi integral minus infinity to infinity f of p, we have 2a by a square plus p square e power minus ipx. E power minus ipx can be written like this. Using that formula cos ax plus I sin ax, we can write this one as cos px minus I sin px dp. Because we have minus here, you will get minus. Okay, now split this one into two integrals. These two get cancelled. Split this one into two integrals. 1 by pi integral minus infinity to infinity a by, you can keep a also constant, a by a square plus p square cos px dp. Another one, integral minus infinity to infinity a by sin px dp. Here a square plus p square also there. A square plus p square. Now using this formula, using this one, integral minus a to a f of x dx equal to 0 if f of x is odd, to integral 0 to a f of x dx if f of x is even. Using this, sin is odd always, cos is even. Sin is odd, cos is even. So then what happens? This total term becomes 0 because this is odd function, this is even. So in even function, what happens? You will get 2. Here f of x is this one, e power minus a mod x. 2 you will get 2a by pi. 2 integral 0 to infinity if it is even. 2 integral 0 to infinity cos px by a square plus p square dp. So finally integral 0 to infinity cos px by a square plus p square dp equal to pi by 2a e power minus a mod x. So this one we need to prove from Fourier transform. Integral 0 to infinity cos px by a square plus p square dp equal to pi by 2a e power minus a mod x. Okay. Find Fourier sine and cosine transform of f of x equal to e power minus ax by x, and deduce that e power minus ax minus e power minus bx by sin sx dx equal to tan inverse of s by a minus tan inverse of s by b. Here, instead of taking p, I taken parameter s. That is notation. Generally, we are taking here p for representing sine transform, cosine transform. In the place of p, you can take s also, no problem, like in Laplace transform. In Laplace transform, we prefer s, here p, no problem, anything. You can do the problem in p, at the end you can replace p by s, you will get this answer. So first, we need to find Fourier sine and cosine transform of f of x. What is Fourier sine transform of f of x? Fourier sine transform. Fourier sine transform of f of x is represented like this. Fs of f of x is equal to integral 0 to infinity f of x into sin px dx. So here the given f of x is e power minus ax by x. Given f of x is e power minus ax by x. So write in the place of f of x e power minus ax by x sin px dx. So now we need to integrate this one. We can write this one as fs of p also. We need to integrate, but not possible to integrate because we have in denominator x. So to integrate easily, we need to cancel this x. We need to eliminate that x. How we can eliminate? By differentiating with respect to p. If you differentiate with respect to p, differentiation of sine px, you will get x cos px. So that we can cancel that x. At the end, if you integrate again, the differentiation get cancelled, because differentiation and integration is reverse process of differentiation. Inverse differentiation only we are calling as integration. First I am integrating with respect to p. Here with respect to x, that's why integration won't be cancelled. So now d by dp of fs of p equal to, so differentiate p term only. If you differentiate, what happens? Differentiation of sine px. Differentiation of sine px. X cos px dx. X get cancelled. So what is left over term? Integral 0 to infinity e power minus ax into cos px dx. This is formula, direct formula. Integral 0 to infinity e power minus ax into cos bx dx. This one we have direct formula. Integral 0 to infinity e power minus ax into cos bx dx is a by a square plus p square. This is direct formula. After evaluating integral and substituting upper and lower limit, you will get that one. So you can write this one directly, a by a square plus p square. So what we got now, this is differentiation with respect to p. But we need fs of p, we don't want differentiation of p. So to eliminate this one, integrate with respect to p. Integrate with respect to p. If you integrate with respect to p, this differentiation get cancelled. So what you will get? Fs of p equal to integral a by a square plus p square dt. So there is one integration formula. Integral 1 by a square plus x square dx equal to 1 by a tan inverse x by a. This is integration formula. Here also a is a only. So a into 1 by a tan inverse p by a get cancelled, plus c tan inverse p by a plus c. But when p equal to 0, c becomes 0. That's why Fourier sine transform of f of x, what is that? E power minus ax by x is equal to tan inverse p by a or tan inverse s by a. Now we know fs of f of x, Fourier sine transform of f of x is integral 0 to infinity f of x into sine px dx. Let take f of x, this one. To prove this, f of x is e power minus ax minus e power minus bx by x. Write that one in the place of f of x. Integral 0 to infinity e power minus ax e power minus bx by x sine px dx. Split this one into two integrals like this. Integral 0 to infinity e power minus ax by x sine px dx minus integral 0 to infinity e power minus bx by x sine px dx. So this can be written, this is Fourier sine transform of e power minus ax by x. That one we just now we evaluated. This is Fourier sine transform of e power minus ax by x, just now we evaluated. This can be written like this. This is nothing, e power minus ax by a. This is also nothing, this is e power minus bx by b. So now Fourier sine transform of e power minus ax by a, we have tan inverse of p by a minus tan inverse of P by B. Now replace P by S. If you write in the place of PS, you will get the required thing, tan inverse of S by A minus tan inverse of S by B. Which one equal to integral 0 to infinity e power minus ax minus e power minus bx by x into sin sx. Actually we have sin px. Here in the place of p, if you write s, you will get that one. This is what we need to prove for first derivation. But we need to find Fourier cosine transform also. So here we need to repeat the same procedure for Fourier cosine transform. How we did like that, again we need to repeat for Fourier cosine transform. Just now we evaluated Fourier sine transform and derived one derivation. But now we are not going to derive, simply we are going to evaluate Fourier cosine transform of f of x when f of x is e power minus ax by x. So here formula will be like this, cos px dx. Here f of x is e power minus ax by x, cos px dx. Like previous problem, we cannot integrate this one also with respect to x because we are having x in denominator. To eliminate this x, differentiate with respect to p again. So what you will get? D by dp of fs of p equal to integral 0 to infinity e power minus ax by x. Differentiation of cos px with respect to p. Differentiation of cos px minus sin px. Again differentiation of px, you will get x dx. This x get cancelled. What is left over term? Minus integral 0 to infinity e power minus ax into sin px dx. This formula, we know this formula. Integral 0 to infinity e power minus ax into sin px dx is p by a square plus p square. For cos we will get numerator a, for sin we will get p. That is only difference. So what you will get? Minus p by a square plus p square. But this is d by dp of fs of p. But we need fc of p. Sorry, this is Fourier cosine transform fc of p. But we need Fourier cosine transform. That means we don't want this d by dp. To eliminate this one, integrate with respect to p. Integrate with respect to p. If you integrate with respect to p, you will get fc of p. fc of p equal to integral p by a square plus p square. This formula we all know. Integral f dash of x by f of x dx equal to log f of x. So using this formula, if you differentiate denominator, you will get 2p. So here if you have 2, you can apply that formula. So now write here 2, multiply with 2 and divide with 2. What you will get? Minus 1 by 2 log a square plus p square, limits 0 to infinity. If you write upper limit infinity for log, it won't exist. Log infinity does not exist. So leave it. Minus lower limit. That means 0 we need to write. So if you write in the place of p0, what you will get? Minus 1 by 2 log a square. So like this one can easily find out Fourier sine transform of f of e power minus ax by x and Fourier cosine transform of e power minus ax by x. Okay, any doubts you may express. Here no need to substitute limits now. Here no need to substitute limits, problem ends here. Log a square plus p square, minus 1 by 2 log a square plus p square there itself. Here no limits, simply integration, no limits. Okay. And Fourier sine transform of e power minus mod x And hence evaluate integral 0 to infinity x sin mx by 1 plus x square dx. So now Fourier sine transform. Fourier sine transform of f of x is capital Fs of f of x, which is integral 0 to infinity f of x sin px dx. F of x sin px dx, where f of x is f of x equal to e power minus mod x, and we know that mod x equal to plus x in 0 to infinity. So mod x is plus x in 0 to infinity. So using this, we are writing e power minus mod x as e power minus x sin px dx. And also we know that integral 0 to infinity e power minus ax into sin px dx equal to p by a square plus p square. This is formula. So the same one, but here a is 1. In that formula, write in the place of a1 p by 1 plus p square. This is Fourier sine transform of e power minus mod x. After finding Fourier sine transform of e power minus mod x, we need to evaluate this one. To evaluate that one, whenever we have deduction along with sine transform or cosine transform, we need to use inverse Fourier. So now we are going to use here inverse Fourier sine transform. We know what is formula for inverse Fourier sine transform. Inverse Fourier sine transform. Fourier sine transform equal to 2 by pi integral 0 to infinity f of p into sin px dp. F of p into sin px dp. This one will be f of p. This is f of p. So now write in the place of here f of x is e power minus mod x. Integral 0 to infinity f of p is p by 1 plus p square sin px dp. So here nothing. In the place of p we have x. What we need to prove? See, this one we need to prove. Here in the place of p we have x, and in the place of p we have x there. Next, in the place of x we have m. Here we have m. In the place of p, see here in the place of p we have x. In the place of x m. What I am saying? Replace p by, wherever you have p, there write x, and x by m. Write in the place of px and write in the place of xm. What you will get? Here 2 by pi I forget. 2 by pi will be there. 2 by pi. 2 by pi integral 0 to infinity. Replace p by x. X sin x, replace x by m, or mx, by 1 plus x square, replace p by x dx. Replace p by x by m. So now what we need to prove here? Here f of x is e power minus mod x. Now we need to prove this value. We need to find this value. Not proving, we need to evaluate this value. Integral 0 to infinity sin mx by 1 plus x square dx. Send this 2 by pi to this side. What happens? Pi by 2 e power minus mod x. Any doubts you may express anywhere. Show that Fourier sine transform of x of f of x equal to differentiation with respect to p Fourier cosine transform. of f of x. So that we need to prove. Similarly, Fourier cosine transform of x f of x is differentiation with respect to p, Fourier sine transform of p. So for that, first I am taking this part, first one. We know that Fourier cosine transform of f of x. We represent that one like this, cosine. fc of f of x that equal to fc of p equal to integral 0 to infinity f of x into cos px dx. This we know very well. Now, differentiating this one with respect to p. If you differentiate, here you will get d by dp of fc of p equal to, here differentiation of cos x minus sin x. Differentiation of cos minus sin. So what you will get? Minus integral 0 to infinity f of x sin px, okay? But with respect to p coefficient you will get here, p coefficient x. So if you observe this one very clearly, we know this formula. Fourier sine transform of f of x, we write like this. Integral 0 to infinity f of x sin px dx. This is Fourier sine transform, we all know. So here, if you have f of x, we write that one as fs of f of x. But here in the place of f of x, what we are having here? X f of x. So we can replace f of x with x f of x. You will get like this, minus fs of x f of x. So this can be written like this, fs of x f of x. Therefore, send that minus to the side, d by dp of fc of p. This is the first one we need to prove. First one. Coming to second one, to prove second one. So first take RHS only. Fourier sine transform of f of x. Fourier sine transform of f of x is fs of p equal to integral 0 to infinity f of x into sin px dx. Differentiate this one with respect to p. Here d by dp. Differentiate with respect to p. If you differentiate with respect to p, what you will get? D by dp of fs of p equal to integral 0 to infinity differentiation of sin cos, differentiation of sin px cos px. Again, p coefficient you need to write here, cos px dx. So we all know that this is formula for fc of p, integral 0 to infinity f of x into cos px dx. So here if you compare, you will have in the place of f of x, x f of x. So which can be written like this, fc of x f of x. So finally what you will get, fc of x f of x equal to d by dp of fs of p. Any doubts you may express. This one we need to prove the second one. Anywhere any doubts you may express. Okay.